Got it. All right, so you guys can, let's see, go back here. All right, now I have one more step before I can actually do this. I have to make it so I don't hear my own voice coming back in my headphones. All right, mute the live. Perfect. And switch cameras. All right, can you guys see the whiteboard?
Yep.
And you can still hear me fine?
Yep.
Are the words on the whiteboard reversed for you, or are they in the right direction?
They're correct.
Okay, because on my monitor view, they're reversed, and I just was checking to see if, all right, anyway, you guys know that. What do the words say? Oh, hey, these were my thoughts for something I wanted to put in those quizzes that I had you guys do yesterday before I made the quizzes. But I didn't actually use those thoughts. That was an early version. One second, let me clean that a little better. So while I'm standing over here, I can't really see the chat. So if you have something you want to say or contribute, please shout it out. Don't type it in the chat. And I suppose if somebody sees that someone has typed something in the chat because they forgot, volunteer to shout it out for them to let me know. I would like this to be a little bit interactive as we go through this. And I'll ask some questions, so please volunteer answers when I ask questions. All right, perfect. So as I said just before we got started here, the process of going from idea to physical part to having a thing in your hand first involves doing some design stuff, right? And so the design part of the job, it's, let's say this is the physical part that we want to have. The first thing we have to do is we have to understand, what are the physical properties of this part that we want to have. And so those are things like shape. Right, so we've got to have the shape, and so shape, geometry. And then there's like the material properties, the mechanical strength and things like that. So it may be strength, hardness, ductility, and all those kind of things. And so those are the things that determine whether or not the part works in operation, right? Those are the things that make it so that the thing you've made meets its intended function. All of this, and so those come out as like specifications and drawings and solid models. Right, so these are the things that you have to have in order to create the part. I call these things the art, or I guess this part of it down here is the art, right? This is the needs. Often we call those the customer needs. So these are the things it has to fulfill This is the art that defines those things. And all of this is done by the designer. And it's the designer's responsibility to create to understand what the needs are in order to satisfy the desired function, to understand those things, and then to create art that clearly defines that. And that whatever that design is, it has to clearly express everything needed in order to fulfill those needs. So that's the designer's job. And it's up to the designer to create that art. What we want to do once that art has been created, once we know what the specifications are, once we have drawings and solid models and other material specifications, things like that, it's our job as manufacturing engineers to figure out how do we take that art and make it into the part, the physical thing that the customer wants. And for several years, I operated a small CNC job shop, a machine shop that made parts like this for people. And at the beginning of that process, what happens is somebody will send you their drawings, or they'll send you their solid model, and they ask you for a quote. And so I actually focused a lot on how do you create those quotes? How do you know how much it costs to make the parts? And also, how do you know how much the customer is willing to pay? Because that's totally part of the quoting process. I spent a lot of time worrying about that and thinking about it. And we made software to automate it and all those things. And what I finally realized, though, was when the customer asked me for a quote, that's not what they want. When the customer asks me for a quote, what they want is to hold the part in their hand. They really don't care about the quoting part of the process. They care about having the part. And so, of course, they may be concerned about how much the part costs and things like that. So it's still something we have to do. But how do you go from the art to the part, the finished part? That's what I want to focus on right now. And so, as somebody in the group, shout out to me, what are the things that the art must contain in order for us to have enough information to even go from the art to the part?
At least one dimension.
So it has to have dimensions. Right, and it possibly just needs one, but it has to have dimensions. What else do we have to have in order to get from art to part?
Tolerances.
Tolerances on those dimensions, right? And so the tolerances, for anybody that doesn't remember, the tolerance is, so I'm guessing that if you don't remember what dimensions are, you could figure that out. Otherwise, you wouldn't be watching this video or in this class. But for anybody that doesn't remember what tolerances are, the tolerances are how much the designer has said we as the manufacturers are allowed to screw up when we make the part they asked for. So that's how much leeway do we have in order to screw up when we're making the part. So we need dimensions and tolerances. What else do we have to have in order to make the part? Do we need anything else?
Material.
So we need to know what material to make it out of. There's a bunch of different ways the designer might specify that. They could specify specifically it's got to be this alloy, it's got to have this percentage of this in it. Sometimes they're more vague on that, but we have to know the material, and that sort of defines the material properties. Like I suppose it doesn't necessarily define hardness and things like that. It could be some material processing that gets it to that. Is there anything else that we have to have from the designer before we can start?
Yes. Oh, sorry.
Go ahead.
Part volume, like how many you need to
So
make.
how many? All right. Anything else that's really important?
Not sure if this is super important, but like a time frame as to when they need it done by, because that could limit what processes you could use.
Yeah, certainly if you're operating it as a business, if you're making stuff with the intent to sell it to people, so you're doing manufacturing in that sense, if you make it perfectly and you meet all the dimensions and tolerances and you've got the perfect material and you've got the right quantity, but you deliver it, say you're making a part for a boat and you deliver it 2 days after the boat leaves the port, nobody's going to pay you for it, right? So knowing when and knowing whether or not you can do it, and when often determines the process that you're going to use. Is there anything else that's really critical there? Say again?
Like a budget, like how much it's going to cost, how much the customer.
So I think we can make the part without having the budget, but it could be useful. So there may be some constraints on cost and things like that. But I think if we have dimensions and tolerances, if we know the material, how many we're going to want to make, and when we need to have them finished by, I think that's enough information to get started. Shout out if you think we've missed anything critical here, but I think that'll get us started. Dimensions, tolerances, material, how many and when. And understanding how the cost factors in there may help us decide whether or not we're going to be able to do it. But I think that gets us going. All right, so if we've got that information from the designer, what's our first task once we've got all that and we understand it and we've made sure that we haven't missed anything in our communication with the designer? What's our first task as a manufacturer then once we have all that? What do we have to make some decisions. We have to pick some things. What's the first thing we're going to pick? Or what are some things we have to pick? We can order them later.
The machining process. And what
All right, so we've
process
got to
you're gonna
decide
choose.
on machining processes. Yeah, let's, for the sake of this example, let's just assume we're going to do some kind of machining. So we have to pick, because really, before we pick machining processes, we have to decide on process in general. So we'll say process or processes. That ES. Processes. I don't know if I did that right. Several years ago, I couldn't even spell engineer, and now I are one. So we need to pick the processes. What else do we need to pick? And let's just assume that we're using a machining process. So the designer has specified what material to use, but you said material, and I agree. What about the material that we have to pick?
Properties of the material, like some materials might
The
have different
designer
properties.
picks the material properties and those things that
Like
are
the tool heads
required.
that we'll be using,
Say again?
like tool heads and materials that we'll be using to machine these parts.
So we'll need to pick tooling. And that includes material, geometry, hardness maybe. Right, so we need to pick the tooling stuff. But when we're picking the material to make the part out of, so the designer has told us what material, but they haven't told us which particular piece of material usually. So we've got to pick the stock. And what are properties of stock material that goes beyond what the designer has told us? So the designer has told us maybe use 6061 T6 aluminum. And so that defines sort of the hardness and the ductility and all that stuff. But what is information about the stock material tell us that's not included in what?
There might be certain imperfections in the stock material that you as the machinist would need to evaluate and fix before you start on the part.
Oh, sorry. I think you might have disconnected accidentally.
Oh, whoops.
Right. Wait, you guys don't see Toby in this, do you?
I can't see him.
Nah, he's gone.
He gone.
I give him 5 minutes.
Does he know he got kicked out?
I hope so. I'm gonna try to reach out to him.
Well, hey, my computer turned off. I don't know why. Can you guys still hear me and see me again?
Yeah, we can.
As new. I can't hear. Oh. Where's the other headphone? Now, can you hear me and see me?
Yes.
Yes.
Yeah. Yeah. So mid sentence, my computer turned off, and I don't know why. But I can selfie this, right? Let me find selfie stick. This is exciting. That's odd. There's usually like a selfie stick tripod mount thing right here somewhere. There's all kinds of tripods. No little selfie stick. All right. Nope, I got nothing. All right, I'll hold the phone and talk. Where were we? I think we had processes, stock material, tooling.
I think we left off talking about the stock material.
Yeah, I think so. Hey, Hayden, can you go into? I didn't ever make you a host, did I? I don't think I'm logged in on my phone, so it's gonna. The screen share is showing you instead of me, or right now because I had it on focus view for me.
Is that better?
Not really.
Professor, we can see you right now.
You can see me when I'm talking.
Yes,
Okay, you can see the whiteboard if I hold the phone in the right place.
yes.
Yeah.
Okay, perfect. Let's go with it then. What I can't believe is I get the notice that said we're still live streaming. So even though my computer turned off, it didn't shut down the connection to YouTube. So wonderful. All right, so we get processes, stock material, tooling, and what we wanted about the stock material was the dimensions, the size. Size and shape, right? Of the stock material. And so that's what's different about stock material from the material spec to our thing here. So we got processes, stock material, tooling. Is there anything else we have to choose as we get started here?
Fixturing.
Fixturing. It's the fixturing is how we're going to hold the stock material while we apply the processes to it. Is there anything else that's critical at this step that we have to choose? I think we've pretty much captured everything at this level of the hierarchy. So the processes, if we're going to do CNC machining, what are our choices for processes? The typical choices, right? There's lots of them.
But
Milling,
at the
and
highest
turn-
level, say again?
milling and turning.
So there's milling and turning. Right, and so the difference between milling and turning really is pretty simple. The physics are completely the same. The difference between the two processes, though, is in milling, the tool spins, and then it moves in X, Y, and Z relative to the workpiece. And in turning, the workpiece spins, and the tool moves in typically X and Z relative to that spinning workpiece. And so turning operations are very good at making axisymmetric parts, making like a pawn from a chess piece, or a pawn or a bishop, if you do the basic shape of the bishop, right? And milling is really typically good at making axisymmetric parts, at making prismatic parts. So turning is good for axisymmetric parts. Milling is good for prismatic parts. So things that where you'd hold a block and cut it into some shape. Now the prismatic parts don't have to have only 6 sides like a cube or a rectangular cube box thing. There's a math term for that. But it does have to have some way to fixture it. And so the first thing you want to do is you want to look at the part you're making and decide which, if we've decided we're going to do CNC machining, decide which of these processes is best suited to make the part. Often, we have to do some milling and some turning on the same part, especially if we're doing a complex part. But so we'll decide the processes, the stock material, the tooling, and we kind of have to decide that process before we can figure out the fixturing and the tooling. Sometimes our choice of stock material helps define what process we choose. Those things are all things that we have to decide. So let's focus now on one of the machining processes. You guys want to focus on turning or milling?
Milling.
Somebody pick one. Milling, okay. So again, in milling, the tool rotates, so the tool spins around. It comes down relative to the part, it moves in X relative to the part, it moves in Y relative to the part. And so as it does that, it basically carves out a shape. And so if you remember that example part I was holding up before, so this is a shape that was made, and so you see it's got a slope there on the top. It's sort of angled this way. It's got a round end here. It's got a bunch of holes in it. It's got features on both sides. If we zoom in here, you see that those corners are radiused over also on that top edge. So if we're going to think about doing milling for this part, and let's assume our stock material is a shoebox that this part would fit in. And that's a term that I commonly use. I've heard other people use it too, so it may be an industry standard term. If not, we'll say it often enough that it becomes an industry standard term. So if the stock is the shoebox that this part fits in, what's the first operation you think we want to do as we make this part?
I would probably start with the bottom of it, or I would assume
So we're
that.
going to start with this side that we assume is the bottom.
Yeah, because that would be.
In actual function, when the part was installed, this is the inside, not really the bottom.
Okay.
It was installed in this orientation.
Yep.
And,
So
and two of these, and there was stuff in between them. But sure. All right. So we're going to start with this face. And then do you want to make the holes first, or do you want to make the odd shaped pockets first?
Correct me if I'm wrong, but wouldn't it be best to start with a facing operation for something like that to make sure that's a smooth surface?
I was going to say that. as well.
So with this particular part, the customer didn't care. And if you, I mean, it's got fingerprints all over it, but you can see that that's actually the as rolled surface from the manufacturer when the stock material was made. But yeah, you might start with a facing operation to get a nice smooth surface there. In this instance, the customer Actually, the most important thing with these parts was the when, not the cost, not anything else, not the how, any of that stuff. The customer didn't care. The customer cared about when, because they asked for them late Sunday night and they had to have them on Tuesday morning. And they had to ship across the country. That was an extra piece. But all right, so if we think about that prismatic material, and so we've got a shoebox that our part fits in. And so I've drawn a representation of the shoebox on the board here. And if we were going to do a facing operation, that means we're going to take a tool. I'll try a different color. Red for our tool path, right? We're going to take a tool that's going to come down and it's going to move across the top surface here. So maybe in a zigzag pattern like that, to remove just a layer of material off that top surface. What that does for us is it gives us a machine surface. It also gives us a surface that we know is parallel with the XY motion of the machine tool. We know that with the fixturing that we have set up and everything, that surface is flat relative to the machine tool. And so that's very helpful, especially if you were going to do some engraving later on that surface, to know that it's aligned with the axis of the machine. And so let's think about that process as the tool comes down. I guess this direction is down in this diagram, right? The tool comes down. It comes across the surface in this motion pattern. And so what we call that is the tool path. And to create a tool path, we have to know what the tool is. And we have to know what the stock looks like. And what else do we have to know in order to create our tool path?
The tooling?
So yeah, so we have to know what tool we've selected to make the tool path with, and we have to know what the stock looks like, so we know how much material we're going to remove from the stock to get the finished shape. What do we have to do once we've picked the tool and we know the stock? What else do we have to know in order to define that tool path?
Speed of the tool?
Say again?
The speed of the tool moving through the material?
So we're going to have to know the speed. So the speed of the tool moving through the material. You can zoom in here. The speed of the tool moving through the material. So, and there's two speeds we got to worry about here. So there's the speed of rotation. And there's the speed of XYZ motion, right? And so this one we typically call speed. And this one we typically call feed. And so we've got speed and feed. What else is critical in order to define that tool path?
We need to know where the stock is.
So in order to write the code that ends up going to the machine tool, we'll definitely need to know where the stock is relative to the tool and the tool change position. So stock, and typically the way we do that is we define a point on the stock as our XYZ0. And then we write all of the code relative to that position on the stock material. That way we could move that part to a different machine tool and still run the same code as long as we told the machine tool where that XYZ0 is in the process. So we need to know where XYZ0 is. What else do we need to know in order to create this tool path? The speed, the feed, XYZ0.
The amount of material you're removing.
So the amount
Depth
of
of cut.
material you're removing. And so in this case, we're going down into the material and we're going across the material in more than one pass, right? So we actually have depth of cut. And our depth of cut is axial and radial. And so axial means how far down into the material did we go, and the radial is how far over do we step. So let's say that if the tool is this big, and we've got about half the tool hanging off the edge of the material as it goes across here. And then when we come back, we step over half the diameter of the tool again when we come back. So that step over is the radial depth of cut. That's how far we've come over. In the CAM software, we're in the class we're going to use a spree. In a spree, they call that step over, and this axial depth, they call that incremental depth. So how far down do you go? If you say we wanted to remove an inch of material off this piece, we might not do it all in one pass. We may come down, make our zigzag, then come back and make another zigzag again and remove that material in layers from the part. So for our tool path, we've got to have a tool, we've got to know about the stock material, we've got to pick an XYZ zero, we have to determine the speed, and the depth of cut. When we figure out the speed, and depth of cut, and I always say that those are the three most important parameters in CNC machining is speed, depth of cut. When we pick those things, what are they based on?
Size of the tool.
So it's going to be based on the size of the tool, so the tool diameter and length, and the depth that the flutes go to, right? So if the flutes only go down an inch, but the tool's 2 inches long, you don't want to cut 2 inches deep because you don't have cutting edges on the tool all the way up that far, right? So the geometry of the tool, size, shape, geometry of the tool, what else is it going to depend on?
Isn't it mainly based on the material?
It's based on the workpiece material and the tooling material combined with the tool geometry and stuff. And so if you have a bigger diameter tool, for example, will take a higher cutting force. And so the cutting force is directly related to the size of the chip we make. The size of the chip is directly related to the axial and radial depth of cut and the feed rate, how fast we're moving sideways through the material. Oh, by the way, for speed here, we typically use surface feet per minute if we're using American units here. So surface feet per minute, and that's the speed of the cutting edge moving through the workpiece material. And it's mostly due to the rotation of the cutting tool. So speed is feet per minute. Speed we typically do is inches per, either inches per revolution or inches per cutting tooth. And so if you've got three flutes on the end mill, 3 cutting teeth on the end mill, you'll have 3 times RPM would be the number of teeth per revolution. So feed is in feed per tooth, and then depth and both axial and radial typically would be inches if we're using US system. It's millimeters if we're using metric, and meters out here for speed while we're doing that. So to get the tool path, we've got to get these basic parameters: speed, feed, depth of cut. We've got to know what our tool is, know what the stock material is. Now let's think about each tool path. This hand's getting tired. I'm going to switch hands for a minute. Let's think about each tool path and what's common about each tool path. And these things are common whether it's a milling or a turning thing. We sometimes use slightly different terminology to refer to them, but we have to do the same thing. Let's think about the tool path and break it up into chunks, because we have to be able to define each of these chunks as we do this. And so we've got I'm going to just get my thumb out of the way. I'm going to do a top-down view of our workpiece now, instead of that fancy isometric projection I drew last time. We got our top-down view. And so Z is coming straight out of the board towards the camera. This is X. And this is Y. And I think I've got a right-hand coordinate system, right? Y goes to X. I guess Z goes into the board, not away from the board. Ooh, about to lose the battery on this thing now. That'll be fun. I think we can finish. What time? What time is it? I may have to end early if the battery dies, or figure out how to plug in and move the phone around. And I got to figure out why my computer crashed. Here's our top-down view. Let's think about the tool. What does the tool have to do in order to do our facing pass, right? So our tool path was like this. So let's say we're just doing one pass down there. And our tool lives somewhere over here in the machine tool we'll call it in a tool carousel. So what are the mechanics? What physically has to happen in order to make this facing pass? So we know what we want for our feed speed and depth of cut. So we know what parameters to use. But what physically happens? What are the motions the tool goes through in order to make this facing pass? Can you guys still hear me?
Yes, we can.
Yes.
Okay. Just checking because nobody was answering. What's the first thing that has to happen?
The machine has to load the tool.
All right, so we've got to do a tool change.
And then start spinning.
And we've got to start the spindle. And this happens for every cutting operation. There's a tool change and the spindle starts. I suppose if you have a machine that doesn't have a tool changer, the tool change happens manually, but even then it happens for every cutting operation. There's a tool change and the spindle starts. Then what happens?
The machine would rapid to the start of the cut.
Right, so we got to move from the tool change position to the place so does it go rapid right to the start of the cut?
No.
Or does it rapid to some position that's a little bit away from the start of the cut, right? And so we got a rapid to clearance position. And every single cutting operation now we don't have to rapid. And when we say rapid, for those of you that haven't seen this before, there's really three different ways that a machine tool moves. Well, besides rotating the spindle, right? So the spindle rotates. I guess that makes it four. But assuming the spindle's rotating, the machine will be programmed to move the tool in a straight line, and so it moves from wherever it is to some predefined point in a straight line at some predefined speed or rate of motion, feed rate. The other way it can move is it can move from wherever it is to some predefined point along a constant radius arc at a predefined speed, or it can move from wherever it is to a predefined point at its best speed. And so when it's moving at its best speed, it's moving in rapid motion. And that rapid motion, you don't control the tool path, and you don't necessarily know the path that the tool is going to take between the 2 points. That can be important when you're doing fixturing and things like that to make sure your fixturing is out of the way for all rapid moves. But we typically move in the rapid motion when we're not intending to cut the workpiece, when we're moving between cutting operations from the tool change location to where the workpiece is, or to our clearance position. So the clearance position is typically not touching the workpiece, but somewhere close. And so in our example here, my clearance position is right over here, just off the end of the workpiece. Once I've moved to the clearance position, what do I do next?
Distance to go.
Say again?
Check distance to go. Like,
Yeah, well, actually, if we're operating the machine, we want to check the distance to go while it's moving to that clearance position. And we get to the machine operations, we'll definitely cover that before you guys get in here and crash everything. So we're going to check that distance to go as the tool's approaching the workpiece. Typically, it's when it's moving to that clearance position. Once it's at the clearance position and we think everything's okay as operators, the next thing the tool does is it actually does some feed motion, right? And there's a couple different ways you can program this, but you can have it sort of slowly enter the part and then speed up as it gets in here, or you can have it just go the same speed all the way across. And there's also ways where you can have it maybe come into the part on a radius and then do the thing and come off on a radius. It really depends on, and so what coming in at a radius or coming in slower and then speeding up, what those things let you do is it lets you control the size of the chip as the tool comes in contact with the workpiece. And so it keeps you from suddenly stressing the tool, suddenly stressing the spindle motor, because as the cutting forces build up, it takes more and more power to spin the spindle. And so you'll get longer tool life, you get longer bearing life, the machines last longer if you're a little bit nicer to them when they're coming in and doing that. And so we call this the lead in. So this move to the clearance position is the approach. This is the lead in. And then we have the tool path, and the tool path is to, in this case, it moves to a straight line to some position over here. Then it does this arc to a position here, a straight line to a position here. And again, you may want to slow down as you're coming on and off the part. You may not actually get completely off the part at this point if the tool's like that. I think you guys can see all that I'm drawing. Shout at me if I'm not pointing the camera in the right direction. And so we've got a lead in, we've got an approach to a clearance plane, we've got a lead in, we've got the feed speed and depth of cut for our process. So that includes incremental depth, the amount down, and step over, the amount over. And then we may have a special lead out move. So if we were doing a contour around this part instead of a facing path, let me redraw that. Let's say the next thing we want to do is make a contour around our part. So again, we've got our workpiece. Let's say that's what the workpiece is. And the green is what we want the workpiece to look like. Can you guys see the black and the green there?
Yes.
Perfect. All right. So what we're going to do is we're going to have a contouring path where the tool comes down. Let's say the tool comes down over here. It goes like this. And so in this case, and so that means the tool is going to do this as it goes around, right? The tool doesn't actually get smaller. Well, I guess it does technically get a little bit smaller as it goes around, but doesn't get bigger again if it has gotten smaller. That's just me, right? And so we've got the tool coming down to our clearance point over here. And then our lead in move here is tangent to the direction of motion. And it comes in at that corner, it goes around. So I programmed the center line of the tool. And then here it finishes that, and then it moves out tangent also. So we could have that approach be tangent let's say we, for some reason, couldn't come down at the end of the part like that, and we had to enter the cut at this location. We might have our clearance point be over here, and then we'll come in on a radius to the part. And so for every cutting operation, we have to decide to define feed speed, depth of cut, what tool we're going to use, what stock material it's going to be, how it's fixtured, how the tool approaches the start point, how the tool enters the cut, and then if we're doing this one again, how the tool exits the cut. Every single cutting operation has all of those steps. Is there anything that I've missed that every single cutting operation has? I don't think so. But silence tells me that either you guys can't hear me anymore, or that the answer is no because I asked is anything, or you really don't care. I'm gonna go with I'm gonna go with the answer was no, not that you really don't care. I'm gonna try one more time here to make my computer turn on. Oh no shit, it just turned on. And it opened up all the things, including the YouTube. I don't know if it still stayed connected to YouTube or not. I'm going to try to hit the Zoom link again. Open Zoom. Join with computer audio, like magic. Reclaim host even. Wow.
Magic.
It is indeed magic. Now I'm gonna see if I can leave.
I think you're muted, Professor. Oh.
All right, can you hear me?
Yeah, but we can't see you.
Yes.
Can you hear me?
We can hear you, but we can't see your, or if you're trying to share anything.
Oh. Maybe you can hear me, but I can't hear you because I took the Bluetooth out of my ear when I put the other Bluetooth in my ear. Now somebody say something.
We can hear you.
So-
We cannot see anything.
I think it's fixed. Coming back. I'm back. It's magic. And I got like a workout doing the selfie the whole time. That was fabulous. Where are we on time? It is 10:28. Let me check my schedule and see where we're supposed to be at 10:28. At 10:28, I'm going to share that screen again. At 10:10, yeah, I was gonna be done with that little mini lecture at 10:10, and you guys were gonna go back to your groups. That clearly didn't happen. Let's see, what are we gonna do to fix that? I think what we're gonna do to fix that is I am gonna have you go back to your groups right now. Or in like 5 minutes, have you go back to your groups, and then we'll do the group report back. We're gonna do that. Yeah. It's not gonna work that well. I'll figure it out. Okay. I will have to interact with each group offline in between now and next Thursday's class, because we do not have class on Monday next week because it's a holiday, Martin Luther King Day, right? All right, so do not work. Well, I guess if you really want to, and if it's how you get your joy and it's how you're gonna be happy, then work on this class on next Monday. Otherwise, like, do holiday stuff next Monday and celebrate Martin Luther King and all those things. But in the meantime, I do want you for the end of the hour here, I do want you to go back to your breakout rooms, and I want you to put some more effort into defining what it is that you want to make. And we're going to do this over the next 2 weeks. When I sent you away to the first breakout, I was thinking that we might do 3 weeks, but I want to control that third week and do the CAM automation stuff in a specific way. So we're not going to include the CAM automation stuff in this, but I think each of the groups had a basic idea, except for, I think it might have been group 5 that wasn't sure what you wanted to make. Based on the things that we've talked about already, come up with something that you think you can complete. So you may need to do the design work if it's not already designed. So something that you think you can complete between now and Thursday, 2 weeks from today. We go back to the schedule. Thursday, 2 weeks from today is February 3rd. For next week's group presentation, so next Thursday, January 20th, what I want you to do is have a progress report on your having made the thing. How far along are you? What steps do you have left? We're going to have to work offline interactively with each of the groups, myself and Hayden, to I think there's only one group that actually had a lab monitor in it, and another group that had some friends that were lab monitors, to make sure that you have adequate time using the machine tools and things. And I'll post some stuff here in the syllabus document for how to go about making reservations and things. Anybody that's not already a basic user of the manufacturing labs should take some time before the beginning of next week to go to mfelabs.org and follow the steps to become a basic user. I think most of you did that last year, or in the past if you did ME1800. Anybody that doesn't know how to do that yet, make sure you interact with your group members to figure out how to do that. Let's see what else. All right, so next week's group presentation is going to be a progress report where you report to the class on the progress that you've made on your 2-week project here of making something. We will reach out to each of the groups, myself and Hayden will reach out to each of the groups to get feedback on what you propose to make, and give you some guidance. We may have you scale back. You may be doing something that's a little bit too exciting. Or we may have you scale up and say, hey, I think you should put a little bit more effort into that. Does that sound okay to everybody?
Yeah.
Any
Sounds
questions? Any questions for me before I have you guys go to your breakout rooms? All right, I'm gonna have you, I guess you guys can just go back to your breakout rooms. I didn't close the room, so they should still exist. Go back to your breakout rooms, spend just a few more minutes really defining that, and pick somebody to be the group contact to interact with myself and Hayden to get some feedback on that, and then have that person feedback with the rest of the group. And I guess email me whoever that contact is for each group. Go ahead and email me that you're the contact and what the group has decided to do, and then either myself or Hayden will get back to you with feedback and how we can help you with that process. All right, let's depart to our breakout rooms.
Are we coming back together after?
We will not come back together at the end, I don't think. I will stay on, so if you have a question for me, you can pop out of the breakout room and ask that question and pop back into it.